Welcome to my third lab on gravity. Woohoo! Okay, so let's get started. What is our goal? Well, our first goal is to find the mass of a black hole in a system where we're given the positions of a star in orbit around it. So we found the mass of the black hole to be 1.988 times 10 to the 31st kilograms. That's pretty heavy. Our second goal is to highlight the differences between momentum over time and forces in the parallel, perpendicular, and normal directions. And our third goal is to illustrate our knowledge of gravity and use empiricism to determine the relationships between the object's properties, motion, and the forces that act on it. So, what are we given? We're given a lot of data. We're going to use it in Python to model a star's position as it goes around a black hole. Initially, that's our starter code. That we're given the mass of the star, the time step, and we're given the black hole's position at the origin. And we're told that the only forces that matter are the forces from the black hole on the star and the star on the black hole. But the star on the black hole we won't really need to use, although it is a good application of Newton's third law. And how are we going to figure things out? Through a series of steps. We're first going to manipulate Python code, then we're going to use our fundamental equations to solve for specific variables, and then we're going to conclude from our data. So here are our fundamental equations. Let's start with momentum. It's mass times velocity. Then we have our change in velocity over time, which is the change in velocity over time. Then we're going to move on to our net force, which in this case is equal to the change in momentum over time. And then we have our parallel and perpendicular components, which are respectively equal to momentum over time, parallel and perpendicular. And then we have our parallel equation given to us by George Schatz, the magnitudes of the final and initial momentum subtracted from one another over the change in time, times the direction of the momentum. Then we have our equations relating the parallel perpendicular forces, which we can solve for the perpendicular force later. And then we get into our gravitational law equation, in which we can manipulate to find m1, which will be the mass of the black hole in this case. And you can see the equation right there that we're going to use in Python. So, before we get into the code, these arrows denote the necessary equations for finding the mass of the star. So let's start it out. So here's the code. We put in the star's mass, we put in the black hole's position at the origin, we specified the delta t correctly. I put it in scientific notation. From the video 5.5, George Schatz, we were able to figure out what the delta x and the delta y were. Then we get into our calculation. So here we're calculating the momentums initially and finally, which are the mass times the initial velocity and final velocity respectively. Then we get into the net forces equaling dp dt, which is pretty self-explanatory since it's the only force in this thing. The dp dt equals the net force. Then we're going to talk about the parallel net forces and the perpendicular net forces, and we related them to our equations. Yep, and that's the perpendicular one being highlighted right now. And then finally, we can figure out the gravitation, and that's the last print statement I have. And oh yeah, I changed the arrow scale to accommodate the simulation. And this is the coded form of the manipulated gravitational law equation. And so the differences between forces and momentum over time, parallel, perpendicular, and regular, are that the momentum over time are derived from observation, whereas the forces are acted upon a body in motion. And so I highlighted the system's mass right before this. And here's a what-if question. If we replace the black hole with another at the same position while keeping other interactions out, and the position of the star is the same, what can we conclude? Well, that we can conclude that the mass is the same since we have the same values and we don't have enough information to tell us if anything would change. But judging by the F-net equation, it would have the same mass. So thank you guys for watching, and have a wonderful week or two until we have to do the next lab. See you guys later.